past, when we worked with sequences, we often referred to them as number patterns, and we looked at two specific types: linear number patterns and quadratic number patterns. If you have a look at the examples here, from 19 to 15, we subtract 4. From 15 to 11, we subtract 4. And we notice the same trend here. From 11 to 7, we subtract 4. So when there is a constant first difference, we work with linear number patterns. And the formula that we used was this one. Tn is equal to an plus b. We then looked at a second type of number pattern or sequence, and we noticed that this number pattern did not have a constant first difference. And so when we encountered that, our next step was to look for a second difference that would be constant. And in this case, we can see a second difference of plus 4. Now, when we're dealing with a sequence that has a constant second difference, we know that it is a quadratic sequence. And so we would use this formula. Tn equals an squared plus bn plus c. And so this, we were introduced to linear number patterns in grade 10, quadratic number patterns in grade 11, and now this year we are going to build on that, and we are going to focus specifically on sequences and series. The first type of sequence that we're going to look at is the arithmetic sequence. So just like we did with number patterns, we have a look and we try to identify whether there is a first or second constant difference. So from 8 to 17, I am adding 9. From 17 to 26, another 9 is added. And finally, from 26 to 35, another 9 is added. So we have here a constant first difference. Now, you might be saying, since there is a constant first difference, we are dealing with a linear number pattern, and you are absolutely correct in saying so. But as we start to build on the foundations that we developed in grade 10, we move towards this arithmetic sequence notation in grade 12. And so this is the formula that we will use from here on out. Tn is equal to a plus n minus 1 multiplied by d. And in this formula, we take note of the following. A is the first term of the sequence, and D is the constant difference. So if you look at the example here that was given, 8, 17, 26, and 35, we are ready to substitute. Tn is equal to, in the place of A, I can substitute that 8 plus n minus 1, and then in the place of D, my constant difference there of 9. And then all that's left for me to do is multiply this 9 and collect like terms. So Tn is equal to 8 plus 9n minus 9, and eventually that simplifies to give us 9n minus 1. Let's consider this example. We are given the sequence minus 22, minus 30, minus 38, minus 46, and so on. They then ask us to determine the formula for the nth term. Okay, this is also known as the general term of this pattern or sequence. So the first thing we need to do is figure out if it is a linear, quadratic, or geometric sequence, and we do so by looking for the constant differences. So to get from minus 22 to minus 30, we subtract 8. And what you'll notice is that we are doing the same thing from term to term. So we have a constant difference here of minus 8. Now that we have that, we are ready to substitute into the equation. Tn is equal to a plus n minus 1 multiplied by d. Remember that a represents your first value and d the constant difference. So minus 22 plus n minus 1 multiplied by that constant difference, please be sure to substitute in using brackets, especially when your difference is negative. Otherwise, you're going to run into some sign problems. What's left for us to do is multiply in and then collect like terms. So minus 22 minus 8n plus 8. And once we've collected like terms, we end up with minus 8n minus 14. Next up, they ask us to calculate the value of term 9. So since we have the general term here, we can simply replace the n with the number 9, and that will help us to determine the 9th term. So T9 is going to equal minus 8 multiplied by 9 minus 14. And I pop that into my calculator and I get an answer of minus 86. So if I were to continue this pattern on until I end up at 9 terms, I will have the value minus 86. And then finally they ask us which term in the sequence will equal minus 102. So since we know what our sequence is, it's this minus 8n minus 14, we can simply set it equal to minus 102. And then we solve this equation. So we'll take that minus 14 over. We'll have minus 8n equals, it's going to become plus 14 on the other side. And then we will simply divide both sides by minus 8. And I end up with an answer of n is equal to 11. So therefore, the 11th term will equal minus 102. Here's another example of an arithmetic sequence. We are given 3 terms. 2x plus 9 is term 1, minus 5x is term 2, and minus 1 minus 8x is term 3. And we are told that these are 3 consecutive, meaning they follow after each other, terms in an arithmetic sequence. And then they say to us, determine the value of x. So what they are actually testing here is that we understand the definition of an arithmetic sequence. In an arithmetic sequence, we know that there is always a constant difference, which means that term 2 minus term 1 must be equal to term 3 minus term 2. In each instance, this will simply equal the constant difference. So what I can do is I can take term 2 minus 5x, and I can subtract the whole of term 1, 2x plus 9, and I can set that equal to term 3, which is minus 1 minus 8x, and I can subtract the minus 5x. Okay, essentially what I'm doing is I'm saying the constant difference here will equal the constant difference here. Be very careful when subtracting to use brackets because there's going to be a sign change here and a sign change here. Okay, so what's left for us to do is to multiply this minus into the brackets on both sides, and then we can collect like terms and we can solve this equation for x. So we're going to end up with minus 5x minus 2x minus 9 is equal to minus 1 minus 8x plus 5x. I can then collect like terms on each side, and then what I can do is get all my x's to the left and all my constants to the right. This will help me to solve the equation. So I'm going to end up with minus 7 plus 3x, so that's minus 4x, and minus 1 plus 9 is 8. And then we divide both sides by minus 4, and we end up with the fact that x is equal to minus 2. And now we are ready to answer the next question, which is simply to determine the first 3 terms of the sequence. So now that we know the value of x, we can substitute it in. So term 1 was 2x plus 9. Term 2 was minus 5x. And term 3 was minus 1 minus 8x. And if we work that out, minus 4 plus 9, positive 10 there, and minus 1 plus 16. So that means the first 3 terms of the sequence are 5, 10, and 15. Now let's have a look at another type of sequence, a geometric sequence. So if you look at the example here, how did we get from 1 to 4? We added 3. From 4 to 16, we added 12. And from 16 to 64, we added 48. So we can see that this is not an arithmetic sequence because it doesn't have a constant first difference. Our next step in the process is to look for a constant second difference. So to get from 3 to 12, we would have added 9, and to get from 12 to 48, we would have added 36. So do you notice that there's not a constant first difference and there's not a constant second difference? That means we need to change our strategy completely, and we need to look for a common ratio. In other words, am I multiplying or dividing by the same value to get to each term? Now you may be looking at the sequence saying, that's it. 1 multiplied by 4 gives me 4. 4 multiplied by 4 gives me 16. 16 multiplied by 4 gives me 64. And you are right. We can work out our constant ratio by taking the second term and dividing by the first term. In fact, we could take any two consecutive terms. You could take term 4 and divide it by term 3, and you would end up with a constant ratio. So in this case, term 2 is 4, and term 1 is 1, and 4 over 1 is 4. So we have a constant ratio. Sequences with a constant ratio are known as geometric sequences, and they have the following formula. Tn is equal to a multiplied by r to the n minus 1. And in this instance, a is the first term and r is the common ratio. You could work out the formula then, or the nth term of this sequence, by substituting into this formula. So Tn is equal to, in the place of a we can use 1 multiplied by r, we've worked that out to be 4 to the power of n minus 1. And that can be simplified to 4 to the n minus 1. Let's take a look at some examples. We are given the sequence 1 over 3, 1, 3, 9, and then it goes all the way on to a very large last term there. Okay, and they ask us to determine the formula for the nth term of the pattern. So what we know is that Tn is equal to a multiplied by r to the n minus 1. Since we know what our first term is, 1 over 3, that means we have the a value, but we need to work out the value of r. Now remember, to do that, we need to say r is equal to term 2 divided by term 1. Our second term is 1, and we want to divide by 1 over 3. Now you can either do that on your calculator, or you can remember from the past we used to say in order to divide a fraction we can actually change it to a multiplication question, and then we end up with a ratio of 3. Now that I have an a value and an r value, I am ready to substitute. So therefore the general term here is equal to a 1 over 3 multiplied by r to the n minus 1. Now if you wanted to use your laws of exponents, you could take this a little bit further. This 1 over 3 can be written as 3 to the minus 1 multiplied by 3 to the n minus 1. And then what you could do is you could say, well, since the bases are the same, I'm allowed to add the exponents. So this will become 3 to the power of minus 1 plus n minus 1, which ends up as 3 to the power of n minus 2. The second question they have for us here is how many terms are in the sequence? Well, what I have is a general term, and I know that there is a last term in this sequence of 177,147. And so if I set those two things equal to each other, I should be able to solve for this without any hassles. Alright, it's very important that you're on top of your exponent knowledge, because we are going to deal with that quite a lot in this section here of geometric sequences. When we are asked to solve an exponential equation, we need to get prime bases on either side. So what you can do is you can use the fact button on your calculator to rewrite this large number in terms of prime bases. 177,147 can be rewritten as 3 to the power of 11. Now that I have the same base on either side, I'm allowed to drop the bases and simply solve. N minus 2 is equal to 11. Take the 2 over, and we are left with n is equal to 13. So there are 13 terms in the sequence. Finally, let's see if we can really get our brains working here. We are given the fact that the 6th term of a geometric sequence is 64, and the 10th term is 4. And they would like us to determine the first 3 terms of the sequence. Well, let's put our knowledge to the test. What we do know for sure is that the general term is a multiplied by r to the n minus 1. We can now apply this general term to the information that they have given us. The 6th term is 64. The 10th term is 4. So let's rewrite those terms as equations. So term 6 is equal to a, we don't know what that is, we don't have the first term yet, multiplied by r to the n 6 minus 1. So that can be rewritten as a times r to the 5. And we were told that that is equal to 64. So that's going to be our first equation that we deal with. Then we were also told that the 10th term, T10, is equal to, let's work that out, a, we don't know yet, r to the power of, n is now 10, so 10 minus 1, and that can be simplified to a multiplied by r to the 9. And they told us that that one is equal to 4. And now that we have these two equations, we can actually solve for the unknown by dividing them. So what we're going to do is we're going to take the one with the larger exponent, we always do that, and we're going to write it above the other one. So we're going to say 4 is equal to a multiplied by r to the 9 over 64 is equal to a times r to the 5. Now we are ready to solve. 4 divided by 64 is going to simplify and give us 1 over 16. And then what we'll see happening on the other side is that a will cancel with a. And I'm left with an exponential fraction here. R to the 9 divided by r to the 5. When you divide bases, you subtract exponents. So that's going to become r to the power of 4. Now, in order to solve for 4, since it is being raised to the power of 4, I am going to take the 4th root. And what I do to the one side, I do to the other side. This is simply going to give me r on the right-hand side, and on the left-hand side, the 4th root of 1 over 16 is a half. So we now have an answer for r. I can then choose to substitute this r value into one of the equations that we were given. Either 64 equals ar to the 5 or 4 equals ar to the 9. It doesn't really matter which one we use, so I'm simply going to choose the first one, and I'm going to say 64 is equal to a multiplied by a half to the power of 5. And then in order to solve for a, I'm going to need to divide both sides by a half to the power of 5. This gives us an a value of 2048. And now that I know what a is and I know what r is, I am able to answer the question. They wanted the first 3 terms of the sequence. So a is always my first term. So term 1 is going to be 2048. Term 2, seeing as though I have a constant ratio of a half, I can simply take this 2048 and multiply it by a half. And that will give me 1024. And finally, term 3, I will take 1024 multiplied by a half to give me 512. And there we have the first 3 terms of the geometric sequence.